Before I start flashing formulas, I want to introduce some context of my talk, which is broadly similar to the context of Tom Hartman's talk on Tuesday, so I'll use that as a start. I want to understand quantum gravity in 3 dimensions. That's the motivation. And we know that classical gravity, semi-classical gravity in 3 dimensions is well defined. You can calculate contribution of any manifold with a metric. But then when you try to calculate the partition function of gravity, let's say torus partition function, we know that there are some problems. There are some quantities which should be positive and they're not positive. And that was mentioned by Luca yesterday. So we need to do something about it. And there are several proposals in the literature which tell you that if you start adding contributions from off-shell geometries, non-hyperbolic geometries, then it seems like the problem goes away, but we don't have a systematic way to do that. So my motivation is try to understand if we can devise a systematic way to sum over all of those topologies and get something meaningful. But to solve this problem, I need to take a step back. And instead of thinking about gravity, which I will not be able to solve right away, I want to have a model which is completely well defined and will allow me to solve some of our topologies and deduce some lessons. Let me see if my pointer works. So my model will be as follows. I will start with a 3-dimensional topological field theory. And I will try to sum that over all possible topologies. This model is similar enough to 3-dimensional quantum gravity because 3-dimensional gravity, at least at the classical level, is a topological theory. So starting with something topological sounds like a good start. And my motivation behind this toy model is this set of papers which try to do what is done in these papers. You can try to interpret in this way. So before I try to make connections with these papers, let me try to explain what my toy model will be. I will start with a 3-dimensional topological field theory. And you can think about Chern-Simons with a compact gauge group. And this 3-dimensional theory, you can calculate the path integral of this 3-dimensional theory on any 3-dimensional manifold with a boundary. This is an example of such manifold. This is a simple handle body, but you should think about more complicated 3-dimensional manifolds with a boundary. And corresponding path integral is a wave function. And this wave function will be a linear combination of 2-dimensional conformal blocks. So I'm talking about a rational example where 3-dimensional, let's say Chern-Simons calculates conformal blocks of some particular chiral algebra. So that's my setup. Now, what I will try to do then, I'll try to sum this model over all possible topologies, and I will devise the measure and get the result. And then now I want to explain that this is, in hindsight, is similar to these papers. The original paper by Maloney and Witten, they were trying to sum over all classical subtles, but mathematically they started with the vacuum character of Virasoro, just summed that over SL to Z. And in a sense, I can interpret what this paper did is saying that I have something like Virasoro TQFT summed over all solid tori. And then I will try to, in the end of my talk, return back to this setting and try to see how I can improve it. Then there was another paper which certainly motivates my talk today by Alejandro Castro and collaborators, where they started with rational model, the Ising TQFT. It's a Virasoro TQFT with a central charge 1/2, where you have a finite dimensional Hilbert space. And they sum that also over solid tori, and they get something interesting. But there were limitations. They saw that if you start with some other minimal models, things don't go very well. And in particular, if you try to sum that over all solid tori, the result, it will be modular invariant by construction, but it will not be positive or something like that. Now, what I want is the following. I want to devise a way to sum over all topologies such that the result of this sum will be physically meaningful. Physically meaningful means that I want that to be an average over CFT partition functions. I want each term in this sum on the left-hand side to be a partition function of a well-defined CFT, not just mathematical modular invariant, but what I would call physical modular invariant, a CFT, which can be defined on any Genus Riemann surface. And therefore, I will start with a unitary theory in 3D. So I want this to be unitary CFT. The density of state is positive. And I want these weights. These are probability weights, but I don't require them at this point to be, the sum of them doesn't have to be 1. But what I want this to be is that I want them to be all positive. Okay, there will be a number of terms in this sum. I, on purpose, call this index alpha to make connection with Dan Harlow's talk. This is the alpha parameter. These CFTs are essentially alpha states in this ensemble holography. So making connection with Dan's talk, these are alpha states. Okay, and then 2 years ago, we were proposing or conjecturing that something like that can be done in general, for general three-dimensional TQFT. And we didn't use the language of alpha states, but we basically identify that what will emerge on the left-hand side, or what you want to emerge on the left-hand side, are CFTs, which are well-defined in terms of three-dimensional theory. So these are what is called maximal gauges, or if in terms of anyons, if you think about three-dimensional field theory as theory of anyons, you want to have maximal condensation of anyons, and each maximal condensation defines your CFT or defines your alpha state, if you wish. So this is what I want. This is a wish. Now, how will I get there? I will get there by self-consistency condition. I will start with the observation that if I have a CFT partition function on a Riemann surface of genus G, I'll start degenerating this Riemann surface. This is a Riemann surface of genus 3. I can degenerate in a Riemann surface of genus 2. This is a very, very narrow bridge, which I will make infinitely narrow. And at some point, my partition function simply factorizes. And then what I can try to do next, I will try to degenerate this torus into a circle. And if I do that, the partition function on a torus will simply become a vacuum contribution. So something universal. So the level of a CFT factorization is a completely straightforward thing. But apparently, what is simple on the boundary side will be somewhat non-trivial on the bulk side. If I now have an ensemble of theories and I try to do genus reduction for all of them, well, they all will factorize. And this factor is completely universal because all of these theories in the ensemble share the same vacuum. And therefore, the ensemble part, the average partition function, will trivially factorize. So that will be seamless reduction from genus G to genus G minus 1. In mathematics, if you're working with the modular forms, there is a name for that. But then let's see what happens on the bulk side. Well, on the bulk side, I cannot explain this formula yet, but I'll just try to say the following. Morally, if I manage to achieve something like that at large genus, then I'm completely set for all genera, for all smaller genera. Because as soon as I have this identity for some G, all smaller G are covered because I can simply do genus reduction. So if I try to devise something like that by summing over topologies, I would rather aim to enforce this at very large genus. If I can do that at infinite genus, then I'm all set because the rest can be obtained by genus reduction. Okay, so this is my goal, and I will do that. I want to achieve this equality at infinite genus. But at infinite genus, this is very easy to achieve. And I'm skipping technical details, but apparently, if you just sum over handle bodies, infinite genus handle bodies, then you will have this equality at this infinite genus. Okay, so in the end of the story, this is the formula I have. There is some unfixed normalization coefficient, which I will fix on next page. But this is what I have in the end. I have a path integral of my three-dimensional theory on some very large genus handle body. And then I apply all mapping class transformations to the handle body. I don't distinguish between mapping class group and this group because I assume that I'm only acting on one cycles. This might be an infinite sum. We will deal with that infinite sum a little bit later. And then I, after that, take degeneration limit, which means that I take my modular parameter to be block diagonal, and these dots shall be taken to plus I infinity. I should take the imaginary part of this matrix to have all eigenvalues equal infinity, okay? Now, I'm not trying to understand if this is finite or not. I assume this is finite. And in my cases, it will be finite because my three-dimensional theory will be simple enough. It will have finite dimensional Hilbert space. So everything will be well-defined. So this is my proposal, but it doesn't look like something I can interpret really as a sum over three-dimensional geometries or topologies. It looks like I started with a very large genus handle body, and I sum over all such handle bodies, and then I will start doing degeneration. I will start making this handle body look a little bit like this. But there is a nice way to interpret that if I rewrite that in the more sort of quantum mechanical language. At least that helps me. And I'll use the bracket formalism to describe the same formula. So this is a rewriting of the same formula as before with certain normalization factors restored. So I have the same ensemble as before on the left-hand side. Here, I'm taking a limit of very large genus on the right. So this is a finite genus. G prime goes to infinity. This is an infinite genus. I'm averaging over the mapping class group. And that is very similar to what Luca was telling us yesterday. But my understanding is that Luca was summing or averaging over mapping class group of the left-hand side. He was acting on the finite genus part. What I want to do is to go to infinite genus and average over infinite genus mapping class group. And the fact that this is average is very important. That will make things finite. Just the sum like this will almost always diverge, but this will make it finite in cases if the Hilbert space is finite dimensional. And then what is written here is the following. The vacuum state is a path integral on a handle body. And then I will take the element of a mapping class group and enact action in the Hilbert space. U gamma is a representation which acts in the Hilbert space. And after that, I have another state. And this state is like a handle body of an original genus with a smaller handle body carved out of it. Okay? So this carving part is maybe a bit difficult to explain. So let me first assume that G on the left-hand side is 0, that I'm actually calculating partition function on a sphere. The partition function on a sphere is a number, is 1, and therefore I'm simply summing up all of these coefficients, and it depends on your normalization. This sum could be 1 or could be something different. But basically, I'm trying to calculate a number. If I try to calculate the number, and this number has good interpretation, going back to Daniel's talk on Tuesday, that's basically a normalization of Hartle-Hawking wave function. And therefore, we can call it alpha, just the same notations I use. Then what I will have here is that I will start with a vacuum in a Hilbert space of genus G prime, and this will be the vacuum of genus G prime. And basically, what I have is that I have a handle body. I act by mapping class group transformation, and I glue it back to the original handle body. What this does is it produces a closed three-dimensional manifold through Higgs splitting. So this procedure literally gives me a closed three-dimensional manifold through Higgs splitting. And my proposal here is to sum over all possible Higgs splittings, or rather average over all possible Higgs splittings. Now it's known that all possible Higgs splittings will give you all possible three-dimensional closed manifolds. So I'm happy about this, because this proposal tells me that I actually will include all possible manifolds in the sum. Okay, that's something nice. And then this alpha is physically meaningful because it calculates something. It's something like the renormalized or regularized partition function of my TQFT gravity. So the model I'm discussing, I should have said that before. I call it TQFT gravity because I have TQFT, which is sum over topologies. So this is like a gravitational model, or topological model. Model of topological gravity, and this will calculate the partition function of that model. Now let me go back to a finite genus on the boundary. Let's say I want to calculate torus partition function. To calculate torus partition function, what you should do is the following. You should produce exactly the same closed three manifolds, but then starting from the high genus Riemann surface, high genus handle body, you should carve a torus inside. And I was trying to visualize that with a faint blue line here, my ability to visualize it is limited, but there is like faint blue line here, which tells you that you should need to carve a torus inside, right? And then if you try to carve a torus inside, what you have is a closed three-manifold with a solid torus carved inside, and that will be a three-dimensional manifold with a torus boundary. Okay, so this is a complicated three-dimensional manifold with a torus boundary, and I'm saying that you need to calculate the path integral of the original TQFT on that three-dimensional manifold. It will not be a solid torus. It will be a complement of a solid torus inside this three-dimensional manifold, and then depending on the complexity of this three-dimensional manifold, this contribution to the torus partition function of your gravitational model could be very complicated. You need to calculate it. But in the end of the story, this is my proposal. Now, I can also comment about this coefficient D. This coefficient D is total quantum dimension of your theory. This is basically the ratio between the value of your three-dimensional topological theory calculated on S3 and S2 cross S1. And depending on how you normalize things, you can absorb this normalization. If you normalize things such that the path integral of your theory on S3 is 1, then essentially you will reabsorb this D and it will completely disappear, okay? Therefore, from going on, I prefer to work in these notations because computationally is more straightforward, but in some way you can remove this coefficient D, and that's the only thing which knew about your theory to begin with. So basically what I'm trying to say is that I devise here a measure which is completely universal. It is not specific to any particular three-dimensional TQFT. And therefore, I hope that I will be able to use exactly the same measure to address the question of gravity in the end of the story. Okay, now let's try to think about what this proposal gives me. So when we devised this measure with Al 2 years ago, the way we were doing that, we were also calculating these coefficients. And these coefficients, which I want to interpret as probabilistic coefficients, they happen to be equal to the norm of some state in the Hilbert space when the boundary Hilbert space when the genus goes to infinity. So that prescription tells you that these coefficients, they will be positive, but we could not make any sense of them. But in some very nice progress, I would say remarkable progress, very recently Ahmed has calculated those coefficients, and he found them to be inverse proportional to the size of the symmetry group of the corresponding CFT. So this is very nice because we didn't put that by hand. That came out as a result of this measure. And this probabilistic weights are correct one in the right sense. These are exactly the coefficients you would see, for example, coming in the Siegel-Weil formula, where you weight lattice-based theta functions with the symmetry of the corresponding lattice. So they're mathematically the right coefficients which you would expect. Here it's the size of the group which is a symmetry group of the corresponding CFT. And the fact that it comes dynamically, or I would say it comes from this measure, is a strong confirmation that this is the right measure to work with. Okay, so this is basically the result when it comes to devising the measure, and this is basically the formulation of this holographic duality, or is this formulation of what I would call TQFT gravity. That's the TQFT summed over all three-dimensional topologies with a boundary with this measure, and it is holographically dual to an ensemble of CFTs. Now, it would be nice to apply that to solve three-dimensional gravity, but that would be difficult to do right away, because of the divergences and because of the computational difficulties, but it would be nice to consider some explicit examples. So one example which we are discussing in detail over last 2 years is an Abelian example, because you can solve it well, and there's actually something to understand in the Abelian case as well. So I'll start with Abelian Chern-Simons theory with a compact gauge group. So the Hilbert space of my TQFT will be finite. It's a simple level K toric code. The conformal blocks on a torus will be some theta function, lattice-based theta function divided by Dedekind function. If you go to higher genus, then here it will be some other universal function, and here it will be higher genus lattice-based theta function. And then in this case, you can ask, can we sum over topologies? Yes, you can do that. And in fact, it's easy to do, because if your K is square free, you actually don't have to sum over all possible topologies. You can simply sum over handle-body topologies, and up to an overall coefficient, the result will be exactly the same. So this simple example is perhaps too simple, and it doesn't really show the need to sum over all topologies, but there still will be an interesting lesson we can learn from here. Okay, so we were writing several papers during the last 2 years, and in a more recent paper we have shown using some representation theory, and there is enough symmetry here, and if you sum over just handle bodies of the same genus, I'm not taking any genus to infinity here, you'll get the correct result. Okay, so in this case you can say this is maybe negating my whole point. You don't need to go to infinite genus, but there is something still interesting to understand, and one thing we can understand from here is the following: what will happen if I take level k to infinity? So first of all, mathematically, this holographic duality can be written in the following sense: the ensemble over CFT partition functions will be a finite sum over Siegel-Narayan theta functions. But apparently contributions from the bulk in this particular model, this is the specifics of this particular model, every contribution in the bulk also can be written as a Siegel-Narayan theta function. But here you have different points in the Narayan moduli space, and that's why you say that you average over different Narayan theories. But when you have a sum over topologies, you instead have different modular parameters. That's a mathematical way of, if you start with this sum, it's not obvious, but if you start with the sum, and here, of course, omega gamma is exactly the same, and you have modular images of this omega gamma, you can rewrite that as a sum over Siegel-Narayan theta functions with different omegas, okay? But then you can ask the question, what will happen if I take k to infinity? Let me ask, how much time do I have? 15 minutes. Oh, wonderful. Okay. So what will happen if I take k to infinity? Well, if you take k to infinity, all of these points will populate the Narayan moduli space more and more densely, and in the limit they will populate it homogeneously with a canonical measure, and therefore you can substitute the sum here by an integral. And this sum will also simplify, and in the end of the story, you will uncover the result of these two works, 2020 works, where an average over the whole Narayan moduli space was shown to be equal to the Eisenstein series, and that was interpreted as a sum over handle bodies of some bulk theory, which was called U1 gravity. So I want to explain what U1 gravity is in some simple terms. It's essentially Chern-Simons theory, but with maybe non-compact gauge group. It's maybe something similar to Chern-Simons theory with the gauge group R. And then there was a prescription given how to deal with the calculations in the bulk. You consider particular handle body, and you calculate only contributions of small fluctuations. So you only contribute the one loop contribution. And if you do that, then the result of your calculation will be this sum, which is exactly the Eisenstein series. And this is the mathematical result in those two papers. And of course, this mathematical result has its own name. It's called Siegel-Weil formula. But those two papers gave a physics interpretation to this result. So what I'm trying to say here is that we uncover this result by taking k to infinity limit. Okay, but there is some message to learn here. I want to emphasize that in my thinking, this U1 gravity, the bulk theory, which is dual to an ensemble of all Narayan theories, I think about it as some sort of prototype to three-dimensional gravity. It's a theory which has certain rules in the bulk, and it tells you how to calculate things, but it's microscopically not defined because the gauge group is not compact. There are some divergences, and the simplest way to see that there are divergences is that if you try to calculate the contribution of handle bodies with sufficiently large genus, if you fix the total central charge of your theory, or if you fix the total central charge of your Narayan ensemble, and you try to average Narayan partition functions for genus larger than certain value, this integral will diverge. This integral is not well defined. And you can trace this in the bulk to the fact that in the bulk, your theory is not entirely well defined, and the Hilbert space of that theory is essentially infinite. And if you put that theory on a closed three-manifold, you will not get any fixed value, any fixed number coming from that theory. Okay, and okay, so there are some divergences in this theory, and this divergence is actually very bad divergences. You can try to ask, okay, now we have some sort of regularized version of this U1 gravity by taking Chern-Simons with compact gauge group and finite level and taking level to infinity. Can I try to understand what will happen if I regularize U1 gravity this way? And you can try to do this calculation, and you will see that if you try to average over Narayan moduli space partition functions for sufficiently high genus, somehow you will have divergent result, and the leading singularity of this result, you'll have something divergent. You will say, okay, I know how to deal with divergences. I will just extract the overall coefficient, which is maybe divergent, but it will multiply something which is meaningful, and I want to calculate something meaningful. So there will be something meaningful, but it will be completely independent on the parameter omega. So I want to emphasize that I'm risking of running. Huh? Right. So I want to emphasize this because I think there might be something to learn about 3D gravity here. So let me go slowly. What I'm trying to do is averaging over Narayan moduli space. These are two-dimensional CFTs, and their partition function depends on the parameter omega. But when I try to do that, I get something singular. When I try to extract leading singularity is not omega dependent. It's actually not dependent on omega. What it is dependent on, it's dependent on the point on the Narayan moduli space, which is counterintuitive because I was trying to average over the whole Narayan moduli space. But the way I was doing that, I started with some discrete model, the Hecke points, and the way how I see those finite number of Hecke points inside this moduli space, I need to start with some particular initial point. So this particular initial point will sort of break the symmetry, and information about that initial point is the only thing which survives, and omega information does not survive. Okay, I know that this is a correct result because it has 5D, 4D interpretation, which I might flash later in my talk. But basically what I'm trying to say is that the genus reduction story, when I try to start with higher genus and then try to take degeneration limit, will not commute with k to infinity. It doesn't commute with k to infinity. In other words, going back to U1 gravity, if you give me this theory, U1 gravity, which is a theory holographically dual to an ensemble of all Narayan theories, and you ask me how can you sum it over all possible topologies, I will not be able to do that. I will get singularities which are too bad to deal with. So basically what I'm trying to say is that semi-classically, U1 gravity is completely fine, and you sum it over tori, and you get something meaningful. You get the Eisenstein series, and that is dual to an ensemble of Narayan theories. But if you try to do from the first principles the sum over all topologies, there is no way to do that. And I think this is qualitatively similar to some of the things we're dealing with in three-dimensional gravity, where certain semi-classical contributions are completely well-defined. But when you try to do the right thing and sum over all possible three-dimensional topologies, you don't get anything meaningful. Okay, so there's something missing. And what I think is missing is an ability to regularize things well. And in case of the U1 gravity, we know how to regularize things. You take Chern-Simons and you make the gauge group compact. And that regularizes everything. You can calculate everything. You can go to infinite genus, calculate everything there. And if you want to take k to infinity later, you can take k to infinity later, already at the level of the torus partition function. With 3D gravity, this regularization is unclear how to do. Okay, I have one more slide where I want to explain the story with regularization in the Abelian case in a slightly different way, but I think it's also intuitive and important. I want to provide this intuition based on the modular bootstrap. So we can forget about gravity part for a moment. We can forget about bulk. You can ask me from the CFT point of view, what does this regularization do? I started with an ensemble over all Narayan theories, but I somehow introduced a regularity K, a level, and instead of the continuous moduli space, I started choosing discrete set of points. How to understand that from the boundary point of view? That's actually easy to understand. The ensemble of all Narayan theories is an ensemble, continuous ensemble of all Narayan lattices. The Narayan lattices are even subdual lattices, and there is a continuous modular space of those. What instead I propose to do, and what instead this Chern-Simons with a compact group does, it tells you that you should be looking for Narayan lattices which are sub-lattices of a particular cubic lattice. It's not entirely intuitive that there will be any Narayan lattices inside this cubic lattice, but there will be, and in fact there will be many of them, and there will be more and more if you take k to infinity, because if you take k to infinity, this cubic lattice will have very, very small spacing. And of course, in the k to infinity limit, you recover the whole space. Now, it's not at all obvious how to prove that, but at least it's not counterintuitive that if you take k to infinity, your original cubic lattice has very, very fine mesh, and you recover all possible Narayan theories. Now, I can, great. I can try to reformulate everything, like I can try to reformulate that in terms of the modular bootstrap constraints. I can simply try to say that I'm trying to formulate all possible solutions to modular bootstrap for theories with this symmetry. And there are two constraints, at least at the level of a torus, there are two constraints to impose. Vectors should have integer length. And important thing, the density of states should be invariant under Fourier integral transform. And what I'm doing here is essentially trading the integral Fourier transform into discrete Fourier transform. And there are a lot of theorems which tell you that discrete Fourier transform would first of all, there are solutions. Important thing that there are solutions to this Fourier discrete transform constraint. And another thing is that if I try to take k into infinity, a discrete Fourier transform will recover back the integral. Okay, so there is a nice and clear interpretation of what happens here at the level of modular bootstrap. And what we said 2 years ago is that that could be a prototype. It doesn't mean that we know how to do it for quantum gravity, but it could be a prototype what is happening for quantum gravity. You need to regularize the solutions for modular bootstrap such that you still have a lot of solutions and stuff like that. I have a slide about 4D5D, which I will skip. And in the remaining 3 minutes, I'll try to tell you what we can do about quantum gravity in 3 dimensions. So can we solve it right now? No, because we don't have a regulator. We now know how to sum over topologies, but we basically don't have anything to sum. Because the original theory, which is like, okay, I can try to solve the Virasoro. That would be a very natural thing to do. That's what I want to do. I want to sum Virasoro TQFT for C larger than 1. But similarly to the case of Chern-Simons with non-compact group, this sum at infinite genus, I don't think it's well defined. It's simply not well defined, and there will be an issue with non-commutativity of the limit. So I cannot really try to calculate the sum first and take this sub-block to infinity. It's not well defined. I need to wait to regularize it. I do not know a good way to regularize it, but there is a first step I can try to do. I can reduce my central charge to be 1/2 when everything is rational. That goes back to the original paper by Castro, Tom, Gabriel, and Pato, and Alex Maloney. But instead of taking 1 copy, I'll take n copies to make things more fun. If I have n copies, my CFT will have very large central charge in the end of the story. Everything is still well defined. I still have a well-defined boundary ensemble. And the partition function, the path integral of this TQFT on any 3 manifold will be a linear combination of conformal blocks of Virasoro TQFT with a C equal 1/2, which is the Eisen model. There are 3 conformal blocks on a torus, right? So this is the model you can try to solve. This is the model you can try to solve. I call it C1/2 to the n gravity, probably the ugliest possible name you can think of. But that's maybe to reflect that this is not quite pure quantum gravity yet. But this is something explicit and solvable. And the boundary ensemble includes all 2D CFTs with this central charge and with this chiral algebra. It's a finite, well-defined ensemble, which is not well understood. For small n, you can construct all of these CFTs explicitly. For large n, there is no known way to account for all of the CFTs, and this is something we are working on right now. These CFTs are not sparse in the conventional sense because the vacuum character of Ising has a lot of states. So you do not expect this ensemble to be gravitationally, to be dual to some gravity with some fields. If you have matter fields in the bulk, there should be order C of those fields. So there should be back reacting on the geometry. But you can do calculations explicitly, and you can average over the mapping class group an infinite genus. And for small n, you can do it explicitly. And I put the check mark to say that this is the check I did. And indeed, you recover an average of the partition functions with exactly coefficients prescribed by symmetry, which Ahmed derived. And that serves a very non-trivial constraint that all of this works. Okay, this is basically where I am right now. Work in progress. I'm trying to take large n limit. When I take the central charge of this model to be very, very large, everything is still completely well defined. And one of the questions I'm thinking about right now, if I calculate the torus partition function soon, the question is, what are the semi-classical, if there's a semi-classical bulk description and what I can learn from this model. Okay, so minute, 2 minutes, no minutes, 1 minute. Well, this is my last slide, as you can see. This is my last slide. So I will first very quickly say what we have achieved, and then I will put some questions to discuss. So what we have achieved is that we started with this well-defined model, which has finite dimensional Hilbert space, and we devised the explicit measure, which is also universal, how to sum over all three-dimensional topologies. So in the end of the story, the measure is completely universal. It's not theory dependent. And therefore, I hope that exactly the same measure will in one day will be applied to three-dimensional gravity, and that will be the end of the story. And then in the case when your TQFT has finite dimensional Hilbert space, we can show that there is a dual probabilistic ensemble of CFTs. There are no issues with divergences. The dual ensemble has finite number of theories. All the coefficients are positive. Everything is completely fine. Now there are questions to think about. One interesting question is ensemble inevitable? I took ensemble for granted here because I have topological field theory in the bulk and wormholes are not suppressed. There is a way to make this topological theory to be dual to one theory only. That will, if you start with a topological field theory, which is sufficiently simple and has no line operators to begin with. But then you can use arguments like typicality to try to see that if your CFT is sufficiently typical, you still should have something semi-classical. There's something to understand there. But I didn't speak about that at all today, so I'll go to other questions. Other question is the following. Is it true that if I sum Virasoro TQFT over topologies, would I really get pure gravity? There are some concerns that Virasoro TQFT agrees with gravity for hyperbolic manifolds and doesn't agree for non-hyperbolic. I would say this is not really an issue for me because if I can define this theory and sum over topologies correctly, I will get a probabilistic dual ensemble, and that will be some interesting physical theory. Whether you want to call that pure gravity or whether there are different versions of pure gravity, that is a separate question. But if that can be defined, that will be an interesting self-consistent theory to think about. But the crucial question to make this work is how to regularize Virasoro TQFT for C larger than 1. To actually make all of the sums, or rather averages of a mapping class group defined. So this is really the question, I think, which we need to understand. And maybe there are no conceptual ways to do it, or maybe there are many ways to do it, and every single way will lead to a particular version. Maybe each version is dual to a particular boundary CFT. That's the version of holography without any ensemble at all. Every holographic CFT will give you its own way to regularize, and that's the bulk theory. And the last question, which I'm thinking about right now, is that how much we can learn from the rational model. So let's say I can solve any rational model, and I have a torus partition function and the two-sided wormhole amplitude and whatever, everything I can calculate. The question is how much you can learn from that. So that's all. Thank you.
So you identified the set of alpha states in this example with the set of gap boundaries of your TQFT. What if your input TQFT does not emit a gapped boundary, for instance, due to higher central charges?
Sure. Then I'll have a rather simple version of holography, where is my master identity? You have nothing here because there are no gap boundary conditions, and this average will average into zero. You'll have phases appearing here, and everything will average over into zero. So there's not much to discuss.
I didn't quite understand how you deal down with sparseness. You want to get a gravitational growth with dark charge, as you were mentioning, right? It's not enough. We need sparseness.
If I want to have pure gravity without any matter or a little bit of matter, I need sparseness, and I don't know how to devise such a model. The model I can devise will not be sparse. The corresponding CFTs will not be sparse. The best I can hope for is a semi-classical gravity with a lot of matter of order central charge, which will backreact. That's the best I can hope for at this point.
So it says something about U1. Is it tractable for SU2?
Eisen is close enough for SU2 at certain level. So yeah, it has been solved, but this is a well-defined problem, and I'm sure it will be solved at some point soon.
Can you just repeat the definition of this calligraphically?
It's a total quantum dimension of your TQFT.
So in the boundary language for the boundary, let's say CFT?
In a boundary CFT, it's not a property of any particular CFT. In the bulk, the best way to think about it is the following. You have TQFT on S3, and you have TQFT on S2 cross S1. So these are two numbers. D is the ratio of these two numbers.
Would you consider symmetric products of minimal models just to get some?
Yeah, that's the great question. This is one of the things I didn't put it on the slide, but this is one of the things which we can try to do next. If you can solve all rational models, it would be natural to try to solve building symmetric product orbifolds, because we know that those have holographic dual. So that's in my research proposal, which I'm writing right now. But I think I will have to solve SU2 at arbitrary level first, and then maybe symmetric product. If you have orbifolds, you have additional lines in the bulk, and the bulk theory becomes more complicated. It's not a conceptual complication, but it's a technical complication. But certainly, this is one of the ways to build toward something where you have a nice holographic dual. Yeah.
Just to make sure I understood your point about the order of limits not commuting, it would be right to say that on the left-hand side of this equality, in the situation where you're averaging over ensemble of CFTs where C is different, that on the right-hand side, you can't necessarily say that this ratio between partition functions calculated in a different genus has like a universal coefficient, and so there's no reason for the G and infinity limit to converge. What's the point between the order of limits to K?
Not entirely sure if I understood the question. Here, all the CFTs have the same central charge.
Right, but I guess that's not a thing that like you know necessarily, right?
Well, in this proposal, it's kind of known. We think we understand how that works now. So you start with the TQFT, which in the dual language is a bunch of conformal blocks. And these CFTs are all possible CFTs you can make out of these conformal blocks. So that's a little bit colloquial, but basically that's what happens. And all of these CFTs will have automatically the same central charge. The issue with non-commuting limits was referring to U1 gravity, which is, in my thinking, is a Chern-Simons with non-compact gauge group. And I was trying to say that that theory, if you try to sum it over tori, that's a well-defined thing. This is an Eisenstein series. But if you try to sum it over high genus handle bodies first, and then try to take degeneration limit, that will not fly. That's what I was trying to say. And that's an indication, in my view, that this is not well defined. And I was trying to make a point that this, I think, is similar to what we're dealing with a three-dimensional gravity.
First time, let's thank